In this module, we will be looking at a popular puzzle and we will see how LTL model checking can be used to solve this puzzle. We will also see a NuSMV demo of this puzzle. The main motivation is to give you an example of LTL formula and some examples of different constructs which I have not discussed before in NuSMV. Here is the puzzle. There is a river and there are 4 things on the left bank. There is a man, a goat, a wolf and a cabbage. There is a boat that can be driven by the man. So here there is a boat and only the man can drive the boat. Along with him, he can take 1 passenger at a time. Okay, so there is a boat which can be ridden by the man and along with him he can take 1 passenger. It could be either goat, wolf or cabbage. So cabbage is considered as a passenger. So each time he goes in the boat, he can take only 1 passenger. The goat and the cabbage cannot be left in the same bank if the man is not there. Because if the man is not there, the goat will eat the cabbage. Similarly, the wolf and the goat cannot be left in the same bank if the man is not there, because the wolf will harm the goat. You might have guessed the question now. How can the man shift everyone using the boat to the right bank? In the sense, how can the man shift everyone to the right bank? The only possibility that he can do is each time he takes the boat, he can only take 1 passenger. Then he can come back, take some other passenger, come back, take some other passenger. On the way, when he comes back also, he can take someone with him. At any point of time, when he is in the boat, he can have only 1 passenger. You might have seen this puzzle before and you can try to think of an answer. Now, what we are going to do is to look at this as some kind of a transition system, and this question would be reduced to a reachability problem. In particular, we will give an LTL formula and we will check this LTL formula on the transition system and somehow derive the way in which the man can shift everyone to the right bank. Yeah, this is what. So we will now see a solution using LTL model checking. Firstly, for the man, goat, wolf and the cabbage, we declare 4 variables which are Boolean. Man equal to 0 means that the man is on the left bank. Man equal to 1 means that the man is on the right bank. Similarly, goat equal to 0 means goat is on the left, goat equal to 1 means goat is on the right. Same for wolf and cabbage. See, the idea is to abstract the puzzle into a way that NuSMV understands. So what we would do is we will declare 4 variables in NuSMV called man, goat, wolf and cabbage, and each of them would be Boolean. The meaning of these variables is that man equal to 0 means he is on the left bank, man equal to 1 means he is on the right bank. Now, there are some other things that need to be modeled. What about the passenger in the boat? We will declare a variable called carry which can take values G, which stands for goat, wolf, W, which stands for the wolf, C, which stands for the cabbage, and 0, which says that no passenger is being carried. Okay? So we want to model the fact that the man is carrying goat by saying that carry is G currently. If the man is not carrying anyone in his journey, then it is denoted as 0. These are the variables What we will do now is to define a transition system where the man can shift passengers from the left to the right bank without worrying about the behavioral constraints. Let us for now not worry about these 2 points. Let's just let the man keep moving passengers here and there. At a time, he can take only one passenger. However, the man can carry a passenger which has the same value as him. For example, if the current value of the variable man is 0 and the current value of the variable wolf is 0, then he can carry the wolf. However, if the value of goat was 1 and the value of man is 0, this would show a scenario where the man and goat are on different banks. Then the passenger that is carried cannot be the goat. So I have given you a rough intuition of what the variables are going to be and what is it that we want to model. So states in the transition system are given by values of these variables: man, goat, wolf, cabbage and carry, and we need to define next of each of them. And how do we define the next of each of them? We see which of the passengers are in the same bank as the man, as in which of the passengers have the same value as the man, and then we have a non-deterministic choice for the variable carry. With all these rough intuitions that I have given, I will now give you a NuSMV demo of this transition system. We will now write a NuSMV code which models the fact that the man is taking passengers right to left, left to right and so on. We will later worry about the path that we want. Let us now start writing the code. As usual, we start with module main. What are the variables? We have 4 variables: man, which is boolean, goat, another boolean, wolf, a boolean value, and the cabbage. Now we need to define the variable carry, which is of an enumerated type. It can take values G for goat, W for the wolf, C for the cabbage, and 0 to denote that no passenger has been carried in the boat currently. These are the variables. As usual in the NuSMV code, after declaring the variables, we need to assign their initial and next values. Let's say that initially all of them are on the left bank. So remember that here we have to say false. It takes true or false. So false denotes that it's on the left bank. Similarly, init of goat is false. Init of wolf is false, and init of cabbage is false. Initially the value of the carry variable is 0. Okay, what we now need to do is, these variables define the state of the system. The values of the variables will tell which passengers are which things are on the left and which things are on the right, and what was the latest thing that was carried. Based on this set of values, we need to define next. What is next of man? See, the man can either choose to stay in the same bank or he can choose to go to the next bank. There is a non-deterministic choice for him. We write it like this: the next value of man is either true or false. Even if we had not written it, it's fine, but we are making it explicit, saying that the next of man is either true or false. What about next of carry? Before writing the next of goat and next of wolf. Let us first write the next of carry because it will be easier. So the thing is, we need to check which of the passengers goat, wolf and cabbage are on the same bank as the man. That means if man equals goat, it means that man and goat are on the same bank, then goat can be carried. Similarly, if man equal to wolf, then the wolf can be carried. Similarly, if man equal to cabbage, the cabbage can be carried. There is, however, a non-deterministic choice if many of them are on the same bank. How do we model this in NuSMV? Let me write it. Case man equal to goat, then the carry could be goat. This non-deterministic choice is modeled by the keyword union. Case man equal to wolf, then the carry could be W. In case union, case man equal to cabbage, the carry could be C. Union 0, which means that nothing is carried. So this is a new thing that I have not talked about yet. So this union gives us a non-deterministic choice for the next value. However, we also need to add this exhaustive case constraint, the statement, otherwise NuSMV would complain. If this is not true, then you can also make it carry. See, this is just to make sure that inside a case statement, the conditions are exhaustive. Similarly here, this just says that the next value of carry is chosen non-deterministically. Either it is the goat or the wolf or the cabbage. However, if it is the goat, then the value of the man should be equal to the goat. If it is the wolf, the value of the man should be equal to the wolf. Similarly, if it is the cabbage, the value of man should be equal to cabbage. This assigns the next value of carry. There is also a 0 which denotes the fact that the man might choose not to carry anyone. Okay? Now, what about the next of goat, next of wolf, and the next of the cabbage? If we write one, the others will be similar. If the goat has been carried, then that means that the value of the goat should change. As in, if the value of goat is 1 and the goat has been carried, then the value of goat should become 0. Similarly, if the value of goat is 0 and it has been carried, it means that the value of goat changes to 1. If the goat has been carried, it should not just be carry. If it is next of carry is G, then we might think that we should, if the value of carry is G, then the goat moves to the right bank, so we have to make it not of goat. However, that need not have to be the case, because carry could be the goat, but the man might choose to stay in the same bank. So instead of putting not of goat, it should be whatever the next of man is. Okay, I will explain it in this case. You can listen again. Here we finish off by saying true goat, case, if the next value of wolf, if the next value of carry is the wolf, then the value changes to wherever man goes next. Okay, if the man stays there, the value remains the same, otherwise it changes. Similarly, if the next of carry is C, then the value of cabbage changes to wherever man goes next. Okay, so this defines a transition system where the man keeps shifting these things from the left to the right bank, from the right to the left bank, and so on. Let's just do a simulation to see that it is indeed the case. Saved it as puzzle demo. Let us now run this file. Let's pick and let's see what the initial state is. There is only one available initial state and all of them are on the left bank. The value of carry is 0. Let's now try to simulate it for a certain number of steps. So this was the initial state, and from this state you can either choose to stay in this state, or you can set the value of carry to be one of them, but still the man can choose to stay in that bank itself. So the variables don't change, the other variables don't change. These are all the situations where carry is assigned to something, but the man chooses to stay here. Now this state is where man moves to the right bank without carrying anyone. This is the state where man moves to the right bank by carrying the cabbage. This is the state where man moves to the right bank by carrying the wolf. That is why the value of wolf has become true, the value of cabbage is still false. This is the state where man is moving to the right and by carrying the goat. Okay? So we can choose something, say man moves to the right without carrying anything. As one would have guessed, from that state there are only two possibilities. So man is on the right and all of them are on the left. He can choose to stay there or he can choose to come here. Of course, he cannot carry anyone. Let's take state 1 where he comes back to the left bank. Now let us say that the man is moving to the right by carrying the cabbage. So man and cabbage will become true. Okay, so let me choose 5. So right now the goat and the wolf are on the left and then the man and the cabbage are on the right. Okay. Now what can happen? He can carry the cabbage back and come back to the left bank, or he can come back to the left bank without carrying anything, or they can just stay there, or this is something which doesn't change anything where he just marks the carry to be C, but the man decides not to change his bank. So you get an idea of what the paths in this transition system are. The paths in this transition system are various options for the man to keep carrying the passengers left and right. Of course, so far we have not ensured the fact that if goat and wolf are left alone without the man, or if the goat and cabbage are left alone without the man, then that is not good. For example, here we indeed saw a situation where somewhere in the state we saw a situation where the man had moved to the right, but the goat and the wolf were on the same side. At least now we have a transition system which mimics this movement going from left, right, and so on. In this transition system, we want a particular path. Let me finish this. So as I said, in this transition system, we want a particular path. What path do we want? We want a path that satisfies the fact that if the goat and the cabbage are on the same side, or the goat and the wolf are on the same side, then man should be in the same side as the goat. This property should be true until the man, cabbage, goat and wolf come to the right bank. You see, this is the kind of path that we want satisfies this LTL formula. Goat equal to cabbage, this is an atomic proposition. Wolf equal to goat is another atomic proposition. This is the NuSMV symbol for OR. We used to write a V-like symbol, right? In NuSMV, we should write it as, write it using this pipe. They say that if the goat and the cabbage, if goat equal to cabbage or if wolf equal to goat, then man should be on the same side as the goat. This property should be true until man, cabbage, goat and wolf come to the right bank. This ampersand is the symbol for AND in NuSMV. So we have a transition system and we have this LTL formula. However, NuSMV would check this property on all paths, right? That's how the semantics of property satisfaction is. A transition system satisfies a property if the set of traces are contained inside the words specified by the property. However, what we want is, clearly every path will not satisfy this. What we want is, we want one particular path in the transition system which satisfies this. So what we will do is, we will check for not of phi. Okay, what we will do is, we will look at this transition system and we will check not phi. If the transition system satisfies not phi, that means there is no path which can do this for us. That means all paths are satisfying not phi. However, if the transition system does not satisfy not phi, that means there exists a path which does not satisfy not phi. That means it satisfies phi. Let me repeat. We want a path in the transition system satisfying this LTL formula. In order to do this, what we do is, we will check for not of this and we will see a counter example to this formula not phi. And what will the counter example give us? It will give us a path which does not satisfy not phi. That means it satisfies phi. Okay, let me check this. There is another way of writing specifications along with the code itself. You can add an extra block called LTL spec, and what we want to check is not of some until formula, right? Not of something until something. And before writing the left hand side of until, the right hand side is man and cabbage and goat and wolf should be true. That means they should be on the right side. And what is the property that should be true until this part? If the goat equal to cabbage, or if the goat equal to wolf, then man equal to goat. So this is what we have. We have a knot of this entire formula, which is a phi until, it's a phi 1 until phi 2, and phi 1 is this formula. If goat equal to cabbage or goat equal to wolf, then the man should be equal to goat, and this formula, this property should be true until man and cabbage and goat and wolf. Let us check this specification. We can do it directly. We just say NuSMV. It says that there exists a counterexample. What we need to do now is to understand this counterexample and form the path. I have copied the counterexample into a separate file and have written the values of variables in every state for clarity. Let us now go through this counterexample. I have also changed the false to 0 for readability. Initially, man, goat, cabbage, wolf are on the left bank and the carry is 0. So this is the counterexample. Let's see. So this has to give us a way of transferring everything from the left bank to the right bank. At the same time, the goat and the wolf should not be on the same side, and the cabbage and the goat should not be on the same side. Let's see. Now everyone is in the left side. Now the man goes to the right side along with the goat. Goat has been carried. On the left side, cabbage and wolf are together. That is not a problem. Now what he does, he leaves the goat on the right side and comes back to the left. Okay, so he comes back to the left and did not carry anything. Now what he does, he brings the wolf to the right side. So man, goat and wolf are on the right side. He has carried the wolf. Now if he goes to the left side and if he doesn't carry the goat, then it will be a problem. So what he does is, he moves to the left side along with the goat, leaves the wolf on the right side. Okay? And now what he does, he brings the cabbage to the right. He leaves the goat on the left, brings the cabbage to the right and leaves it along with the wolf, and then goes back and brings the goat back to the right. Okay? The counterexample actually continues, but we do not care about that. See, the counterexample will give us an infinite path. In the sense, it will give us a path and it will mark loop starts here. However, what we want is, we want a prefix. For our solution, we want a prefix which satisfies this. So, whenever you are checking for phi 1 until phi 2, at some point of time, phi 2 is true, and till that point, phi 1 is true. See, we have got a trace that satisfies phi 1 until phi 2, and this is giving us a solution to the puzzle. What we saw in this module is a way of using LTL model checking to solve a puzzle. This puzzle is part of a bigger class of problems in artificial intelligence called planning problems. In planning problems, you have a set of states and you want to find a path to a goal state with certain properties being satisfied. This is exactly what we did now. We can use LTL model checking even for solving planning problems. This also gives us an example of the use of until formulas. So until can be used to check that something is true until we reach a goal. The reference to this example is this book, Logic and Computer Science by Michael Huth and Mark Ryan. You can also find some other NuSMV examples in this book.